没有吗？现在有 stream 吗？看一下。hello， 看我这样弄有点失败。有了。Okay. So yeah. So anyway, we will have our second midterm next week. As a reminder. Yeah, it's a little tight on schedule. And we'll have second midterm on next week, and next Tuesday we'll probably give a quick review just like what we did for the first time. So a quick summary of chapter 3 and chapter 4. And hopefully we can finish all our other chapters before our final exam. Or Laplace transform. I need to cut out something. But anyway, so let's do our this part of chapter 5 before midterm. So where is it? Okay, yeah, chapter 5. So once again, this time we spend a lot of time doing this derivation, but the important thing to remember is for the discrete time Fourier transform, we have those two equations. So big X equal to summation X e to the j omega n, not surprisingly, and X of n equal to 1 over 2 pi, and now this big X has a period 2 pi. Like we keep saying, because small x is discrete, so big X is periodic, and for here the period is 2 pi, and because it's periodic, so we're only integrating over one interval, and we have this integrating over 2 pi, big X of e to the j omega, then this e to the j omega n you always see, and the omega. And yeah, obviously this e to the j omega n is periodic in 2 pi too, because n is integer value. And this is nice. We also see the convergence relationship. So if x is either absolutely summable or finite energy, then we think the Fourier transform will be converged, usually. Any question? If not, then let's go to we have a lot of things scheduled today. So first is this periodic signal. So discrete time periodic signal and what is Fourier transform. And we do our derivation kind of from what we know in chapter 4. So in chapter 4 we also have periodic signal, and when we try to derive the Fourier transform of the periodic signal, we first look at the Fourier transform of the complex exponential. And in chapter 4, we know the delta function because we do the reverse Fourier transform and find out that it's complex exponential big. Okay? And yeah, so we have this relationship. And now we're discrete time, so we basically guess the answer. So we know the complex exponential will give you some delta function, and delta equal to this omega naught. And we know the big X for discrete time signal must be periodic with period 2 pi. So we just copy everything every 2 pi, because we know there should probably be a spike here, and it should repeat itself. So we copy all those delta spikes with the distance being 2 pi. And if you write down the equation is this thing. And so that's our guess. And once again, we can check it out. Our guess is correct. So we check with our inverse Fourier transform equation. So x of n equals 1 over 2 pi. It's big X times e to the j omega and d omega. And if you do the integral, it's basically the same integral as this thing. This is infinity to infinity, and now you cut to this 2 pi region, then we'll pick up this back here, and they give you back this e to the j omega. Okay. And yeah, so we know the discrete. We know we work with this discrete time signal, then its Fourier transform is this impulse train. Okay. This whole bunch of delta function, all spaced with 2 pi. with spacing 2 pi between them. And yeah. And now if we have a more general periodic function, then first we can write it in its Fourier series. So the summation ak and a whole bunch of complex exponential with omega being 2 pi over n, 2 pi over big N times small n. Sorry, that's not omega. Small n is not part of omega. The omega is k times 2 pi over big N. Okay, so some ak it has omega being the omega naught being 2 pi k over n, and then we know it will be. Then we haven't talked about this, but obviously the Fourier transform in this line is also linear. So for linearity, we know the Fourier transform of this thing, the linear combination, Fourier transform of the linear combination here is just the linear combination of a Fourier transform. So just the summation k from 0 to n and ak 2 pi, and the Fourier transform of this thing is 2 pi and this impulse train. And here so we do this. Now, well, the idea is just use sum over the impulse train, and now we just choose a different form with some. We write this in one interval. So if you cut the summation of those impulse train in one interval, obviously just sum it once. So has this k from 0 to n minus 1, and so just delta omega minus omega naught, and this is for one interval, so omega between 0 and 2 pi. And here, so this equation is the whole thing is we say for one interval is this thing, and it's periodic with period 2 pi. So it will copy itself every 2 pi. Okay, and so this is quite ugly because the describing one interval and saying it's periodic. So we can also write it in a neat equation. Yeah, it's really nice. You can just say you are summing over k from minus infinity to infinity, and this thing. And but ak is only defined between 0 k from 0 to actually well no. Yeah, and before we also for the Fourier series we also have ak being periodic with period big N. So yeah, so we just say so here we only summing over big N terms, and now we are just having sign over infinite terms. So yeah, and the ak being periodic will correspond to this big X being periodic. And we can check a little more that those two are the same thing. So we should check the point where you go from k to k plus n, right? So some a1 to some a1 plus big N. And so those 2 points will have the same ak, so it's 2 spikes with the same height, and it should correspond to here, so it should corresponding to this spike and this spike. So it should come from the same impulse train, and we know the distance is 2 pi. And is that distance 2 pi? Yes, because you check, if you change k to k plus n here, then you have, instead of 2 pi k, you have 2 pi k plus big N over n, and that's just 2 pi plus 2 pi k over n. So you know those two spikes is distance 2 pi, and this equation is exactly describing this equation. Okay, so just some changeable notation, and the idea is you have a whole bunch of ak, and that will give you a whole bunch of spikes, and they will be all in one 2 pi interval, and you just copy paste them all for the future time and for the past time, and it will be periodic. Okay, so that's not too much to say. And just summarizing what we have done as a recipe to get Fourier transform for periodic discrete time signal. So first you have your periodic discrete signal, and you express it as a Fourier series. And so you can calculate the AK once again with your analysis relationship, analysis equation. So this is some xn times minus e to the j omega n, and some normalization. And with this, you can write your xn as summation ak e to the jk omega n, and or jk 2 pi over n small n, and then you can just from this equation directly write down your big X, and just sum k from minus infinity to infinity, and 2 pi ak delta omega minus 2 pi k over n. The 2 pi k over n correspond to this 2 pi k over n. And just like in chapter 3, AK is periodic with period big N. Any question? If not, then let's see an example. Our favorite periodic signal, which is cosine. Okay, and yeah, once again, cosine is e to the x times plus e to the minus x. Cosine x is equal to e to the x. Sorry, cosine x is e to the jx plus e to the minus jx divided by 2. And and here for the omega naught, we pick it being 2 pi over 5. And so this symbol has a period of 5. And yeah, it's, here the Fourier series is super easy. You don't even need to do this summation. You just look at this, and it's already in Fourier series form. And so from here you can read there is a A1 and there is a A minus 1, and the coefficient is plus 1 over 2 and 1 over 2. So yeah, so that's your, and then you can follow this recipe, then you directly write down your big X. So it's 2 pi times 1 over 2, so it's pi and delta here and another delta here. And it should be repeated every 2 pi. So like this, keep repeating. Question? So yeah, that's a Fourier transform of your discrete omega. And also another slightly more interesting example. So it's like impulse train to impulse train. Although, so for the continuous case, remember we have impulse train. If you have a whole bunch of delta, then you will Fourier transform get a whole bunch of delta. So this is similar, but a little different, because now we have discrete signal, and in a discrete time, this delta function is actually a finite thing. Okay? So this delta, remember discrete time delta is a little different from continuous time delta. The discrete delta is just value 1. Okay? Anyway, so we have this kind of impulse train, although it's not quite impulse, or it's impulse but not quite infinity. And yeah, impulse train with the period being n, so whole bunch delta with the spacing between being n, and well, it's still a periodic function, and we can calculate, and obviously the period is big N, and we can calculate the AK, the Fourier series coefficient, and because the delta function is quite easy to see that this thing is 1 for every AK. Okay. And yeah, and if you follow the formula, you will write down your big X is, this is a constant, so big X is also a constant for every point at 2 pi k over big N. Okay. And so that's your big X. It's once again it's an impulse train. So now this is the actual continuous time delta function. It has infinite height with infinity times 2 pi over n. And yeah, it's an impulse train. It has all same height. So you have discrete time in position is changed to a continuous time in position. And once again, if you have higher spacing here, the period here is bigger. If you have smaller spacing here, the period will be 2 pi over bigger. Okay, question? If not, then let's go to the properties of the discrete time Fourier transform. And yeah, you can see we have lots of property. I guess something we can at a very high level talk about the difference to the to chapter 4, right, for the continuous time Fourier transform. So the biggest difference, first thing is obviously the big X will be periodic, and the other thing is obviously you are discrete time, so for discrete time you cannot do differentiation on it. Okay, yeah, you need to do difference, and so that's something different, and also there will be something different when you try to do time scaling on the time domain signal, because for discrete time signal you cannot arbitrarily compress and stretching it, because you must have your function value at your integer values, and we'll see more about it later. For now, let's go through the property one by one. Yeah, so first, as we said, the big X is going to be periodic with period 2 pi. I've talked about this many times, and I don't think we need to prove this again. It's something very important you should remember. And then second property, linearity. Yeah, I think every transform we talk about in this class is linear. And obviously this discrete time Fourier transform is linear again. It's very easy to prove, so I'll skip that again. And time shifting. This is basically the same as the continuous time case 2. So you shift in the time domain, then you get HR e to the j omega n over j omega t. And if you shift in the frequency domain, it looks a little different, but what happens is you change omega to omega naught, and you will get e to the j omega n on the time domain. Okay? And also the derivation is just you substitute different variable to your synthesis equation or analysis equation, and you'll get this. And that's okay. So the derivation is very easy. Now let's talk some application, kind of application. That is now this is only true for discrete time case. That is, you can very easily shift from a low pass filter to a high pass filter by doing some modulation. Well, you can do this modulation shift to your signal. We already see that on continuous time, but for discrete time it's a little different. That is, so for discrete time, remember all the Fourier transform. When you go to frequency domain, everything needs to have period 2 pi. Right? So you have a low pass filter. The low pass filter is also periodic, and it will filter out the frequency around 0 or 2 pi or negative 2 pi, so integer multiple 2 pi's. So it's this periodic thing. And now the high pass filter will filter all. High pass filter is also periodic with period 2 pi, and the high pass filter should filter all these things around the odd multiple pi, right? So like pi, minus 3 pi, or plus 3 pi. And you compare these two, you see this thing shift by a frequency of pi, right? In either plus pi or negative pi, it doesn't matter because it's periodic. You either shift this thing to the left by pi or to the right by pi, it will become this thing. Okay, this is only true for discrete time signal. because everything has this 2 pi periodic, and you have a frequency, high frequency is around those pi, and low frequency is around this 0 or 2 pi. Yeah. Anyway, so so we want to shift from this filter to this filter. Then you can multiply. You can do this. Yeah, and I guess it's still not very easy, but if you you think about if you can do this thing, so you shift back to the time domain, and so you want to get this thing, and because of our frequency shifting property, then you know that so you reverse Fourier transform this thing back to the time domain, then you know the impulse response, which is the reverse. So this small h for this high frequency filter should be e to the j omega n times the impulse the small h of the low pass filter, because of this frequency shifting property. Because we know this thing is the big H of the high pass. So shift back, and you get this HR e to the j omega n, where omega n here is pi. You want to shift pi, and yeah, and e to the j omega n is -1 to the n. Yeah, because sorry, e to the j pi n is -1 to the n, because e to the j pi is -1. So we know in the time domain, high pass filter and the low pass filter has a very simple relationship. You just multiply by this -1 to the n, then you will change from low pass to a high pass, or high pass to a low pass. Okay, and yeah, basically this thing, and you can also shift by a different frequency. Maybe you want to shift by pi over 4 instead of pi, and you can get some band pass filter. Okay, so it's kind of interesting. And then conjugation symmetries, and yeah, this is same as the continuous time. So if it's real, so I guess we start from the conjugation. Once again, you conjugate your signal, then on the frequency domain you need to conjugate and get a minus sign in your frequency. It's the same for every whole possibility of our Fourier Transform or Fourier Series. Okay? And once again, if it's real, that means this thing equals this thing. It's this, and also, then if it's real, and then if it's real, then the even part of your signal will correspond to the real part of your your spectrum, and the other part of the your signal will correspond to the imaginary part of your spectrum. And this comes from the even signal will have even Fourier transform. Yeah, we'll see this a bit later. Yeah. And also, now as we said, now x is discrete time, so we can do differentiation on it. So instead we do difference, and difference is kind of boring because it's basically a linear combination of your frequency shift. So we already know frequency shift, and you do linear combination, so you just write down, you get HR 1 minus e to the minus j omega here. And now the inverse of difference is a little more interesting. Yeah? So once again, the inverse of difference is this accumulation. And just like the integration. So you think about if you do inverse on this side, you will probably also get inverse on this side. So you get this 1 over 1 minus e to the minus j omega big X. but just like doing integration, and when you do the summation, you might get an extra constant term. So you might actually get an extra delta function here, okay? And it will correspond to the DC term of this y. And the magnitude of this delta function is pi and the big X of e to the j0. So, and just like in the continuous case, a good example of this is the unit step function and the impulse function. So we think a unit step function is something that has a DC term of 1 over 2. That's why you get this pi delta function times pi. Okay? And yeah, let's go through this slowly. So first we start with this x of n, which will actually go g of n. And g is a delta function, but it's a discrete delta function, so now it's just finite value 1 and then equals 0 and 0 otherwise. And anyway, you can do the Fourier transform of this thing, and this still give you a constant, because yeah, you do the summation and this thing and all the complex exponential, but this complex exponential at n equals 0 is just 1, and there is 1. And then we use this formula to do our running sum. And so running sum of this delta function obviously give you this unit step function. And the corresponding Fourier transform, so you just plug in the formula, it will be the 1 over 1 minus e to the minus j omega times this your original Fourier transform, and then this pi and this spectrum taking at omega equals 0 times your delta impulse train. And because our big G is just 1 here, so it is 1 over 1 minus e to the minus j omega plus pi and sum over your impulse train. So yeah, that's the discrete Fourier transform of your discrete unit step function. And okay, good. Question, then time reversal, and yeah, time reversal once again is very easy. You can easily derive that if you do time reversal, then you will get frequency reversal. Okay, we actually have derivation here, so just a change of variable. And from here, you can easily see that your frequency domain is an even function if and only if you are even function on your time domain, and also if big X is odd, if only if small x is odd. Okay, just like in the continuous time case. And yeah, so this goes well with your conjugation relationship here for the real and even, the real odd and the even imaginary thing. And we have those false and conclusion from even odd thing. So yes, we should look at for its real, then the even part will correspond to the even part, and odd part will correspond to the other part. And if it's imaginary, then it's flip around. Sorry. Okay. Okay, I think something is weird. So even is even, and okay. So there should not probably be now 3. Let me see. Okay, I think one of these is wrong. Well, I will check this later. Okay. But anyway, let's go to another thing. So we have time reversal, and then now is the tricky part about the discrete time case. We have time expansion. Yeah, and as we said, because now it's discrete signal, so we cannot just do arbitrary scaling of our time. Remember, in continuous time, we can just change x to x of t to x of at, then we'll get some stretching or compression in our frequency domain. But in now the discrete time, then we cannot do arbitrary compression. We basically cannot do compression. So the idea is that it's easier to see this example here. So if you want to stretch out, so our signal is look like this, and we can kind of do stretch out of the signal. Say we want to stretch with a factor of 2, and then this signal will get stretched to this. We can stretch to a factor of 3, then we'll stretch out to this. So you see that you can only stretch out to an integer factor, right? Because if you don't stretch out to an integer factor, then your signal landed somewhere that's not an integer value. Then you can, that's not a discrete signal, that's not allowed. And also you can just not squeeze in your signal, because if you squeeze in, then one of the function value is going to land on a non-integer value. Okay? So you can only stretch out, and you can only stretch out with integer value. Okay? And but we can do that. So we can stretch out with multiple of integer value, and we call that stretch out function x is sub-parenthesis of k. Okay? And on the picture it looks exactly this. So it's 0 everywhere except the stretch out point. Okay? So so if, for example, is k equal to 2 here, stretch out at the ratio of 2. And so when n is multiple of 2, then this x sub k of n equal to x of n divided by k. So for example, this x sub 2 of 2 will correspond to this spike, and the same as this spike. Okay? And yeah, that checks out. So x2 of 2 will equal to x of 2 divided by 2, that's x of 1. And also x2 of 4 will equal to x2, which is x of 4 divided by 2. Okay? So you write the stretch out function in a mathematical form is this thing. And if you do this, so finally this is our relationship. If you do the time expansion, then you will get a compression in your frequency. So you get a sub k here, then you change it from e to a j omega to e to a j k omega here. Get extra k here. And the derivation is not too hard, so we can write down this as the definition. So big X or sub k of j omega equal to, now from our for our analysis relationship, so mention all the n and the xk of n e to the minus j omega n, and then we know this thing only has value. So this x sub k is only non-zero only when n equal to some integer multiple of k. So we say n is r times k, and instead of sum over n, we have sum over r. Also from minus infinity to infinity, then x sub k, then become rk and become rk here. And now we use this equation for on all the non-zero value. A sub k of rk is just x of rk divided by k, which is x of r. So it's r minus infinity to infinity. So now this is x of r, and this thing is e to a minus j. We can just group the k with omega together. Okay? And now this new omega is k omega, and yeah, this is a synthesis equation for the Fourier transform of x of r, and as big X of e to the j k omega. Okay. Yeah, and we've seen this picture a few times, but see this one again. So you have your signal and it's Fourier transform, and when you stretch out, it will get squeezed in on the other side. And stretch out more, and it will squeeze in more. And from the squeezing, you can also see why you want the stretch out to be integer boundable, because you want here to stay having a period of 2 pi. So instead of a period of 2 pi, you need a period of 2 pi divided by 2 and 2 pi divided by 3. Okay. So 2 pi will remain being a period of all the big X. And then now let's see an example of this being useful. Okay, so the question is seeing this quite a few times. You have X of n look like this, and you want to calculate its Fourier transform. Okay, and because we want to use our stretch out thing, so we write it as a sum of two functions that look like a stretch out. Okay, so write this X of n as this 5 point, which is an empty space between them, and another 5 point, which is empty space between them. And we think those two functions as the stretch out of this square wave signal. Okay, so you can kind of see it here. So if you have this signal and you stretch out it with a mod factor of 2, then you have this 5 spike becomes 5 spike. And also if you scale it, so it change from height 1 to height 2, and also do some time delay, you'll get this signal. Okay, so pretty easy to see from this signal to this signal is you change the height to 2 and delay time by 1. And also if you add those two together, you back your X of n. So yeah, so we can write xn as a linear combination of these two. And so we want to Fourier transform this thing, and those two are all come from this y of n. And y of n is basically a square wave signal, right? And we already know how square wave signal works. But when we talk about square wave signal, we have the center around 0. So this is a square wave signal with some time delay too. So we call those rectangular, call rectangular pulse. So rectangular pulse, we call it G of n. And yeah, so this thing has width 5, and when you write in our square wave notation, that corresponds to is n1 being 2. Yeah, right. So this here, so this n1 being 2, and and we already know the Fourier transform of the square wave. This is sine over sine, so we can directly write down the Fourier transform. This is yn. It is sine over sine, and because of a time delay, you get extra e to the minus j to omega here. Okay, it should be minus j omega times 2, and yeah, so it's minus j to omega. And so why is this thing? Then we can do our formula. This what is called? This time expansion formula. And now we have time expansion factor of 2. So basically, then you get k equal to 2 here. So every omega here should be multiplied by 2. So instead of 2 omega for omega here, then if omega, this omega over 2 will become omega. And then you do your scaling to times 2 and this time shift of -1. So the time shift of -1 give you extra e to the minus j omega, and it's times 2 is times 2. Then you add everything together is this equation. Okay. So yeah, so we use our Fourier transform over rectangular function and search it and copy paste and get a Fourier transform of this weird 1-2-1-2 function. Okay. So it's quite nice. And another thing is, well, so this Fourier transform pair is discrete in the time domain, but it's still continuous in frequency domain. So we can still do differentiation in frequency domain, and it's basically the same as the differential property in a continuous time case, and you get the extra minus j omega n, sorry, minus jn here. It was minus jt, now it's minus jn. You can derive this by just differentiating this equation, and somehow we like the j on the other side, so to move the minus j here to a plus j here, and this is our differentiation formula. And the extra slide, just a reminder again. And finally, we have a possible relationship, and yeah, not too much to say. We still skip the derivation. We have the energy at the time domain equal to energy at the frequency domain. Time domain is not periodic, so we sum from infinity to infinity. And our frequency domain now is periodic, so only integrating over one period. And there is still this weird normalization 1 over 2 pi here, just need to remember. And also here we say something a little more about possible relationship, possible relation. So it's a special case of this inner product relationship. And this kind of thing is also true for all other Fourier transform. Okay, so you have this inner product of some function on the time domain, so we send us the inner product in the frequency domain, and yeah. Okay, and finally, now we have this example of test on every property. So we are given spectrum of some function and it's complex, so give you the absolute value and its angle. And now we ask 4 questions here. Is it periodic, real? Is it periodic? Is it real? Is it even? And is it finite energy? Okay. So I guess let's do our 5 minutes, so we can still do this. So yeah, so let's do a vote here. Is this periodic? Raise your hand. If it's not periodic, raise your hand. Okay. So 1 periodic, and if it's real, raise your hand. If it's not real, raise your hand. No one wants to answer. Is it even? Raise your hand. If it's not even, raise your hand. And if it's finite energy, raise your hand. Okay, and if it's not finite energy, raise your hand. Okay, so yeah, now let's see the answer. So first, is it periodic? It's not periodic. So this is the thing we talked about at the beginning of the course. Remember, for it's periodic, then it should be look like impulses, right? So let's see if we can. No, that's too slow. Okay, yeah. So for periodic function, its Fourier transform will be whole bunch of delta function and a periodic placed, right? And obviously there is no delta function here, and yeah, so this is not periodic. And if it's real, it is actually real. So once again, remember our real condition is you take your big X and you take its complex conjugate, and negation on the frequency will back to yourself. So if we think about this thing, when we take complex conjugation, so the complex conjugation don't change the norm. Okay, but when you do complex conjugation, then the angle get a negative sign. So instead of this line, you get this line, right? But then you flip the frequency, so you flip this left and right. Then this line will get flipped back to this line. Okay, so when you do this conjugation, then negation of frequency, the angle will change back, and also when you do conjugation, this doesn't change, and because it is an even function, so when you do negation of frequency, this also doesn't change because it's an even function. So you see that both of these things doesn't change when you do this conjugation and negation of frequency, and so this whole function doesn't change, and that means that your xn is real. Okay. I guess we didn't say this quite clearly, but this relationship, so this if x is real, then this is true, and that's actually infinite non-leaf. Okay, so if this is true, and then x is also real. Okay. Okay. And now is x of n an even function? It's actually not an even function, because as we said, if x of n is an even function, if and only if big X is an even function, and big X is actually not an even function, although its magnitude is an even function, but its angle is not an even function. So yeah, x of n is not an even function, because the angle is not an even function. And finally, is it finite energy? Yeah, it's finite energy because the magnitude is finite, and you can easily integrate over it, and it has a finite energy on the frequency domain. And by our possible relationship, then you can also calculate the finite value for the energy on the time domain. And you just need to divide by 2 pi. And if you actually do the integral, even though we didn't ask you, you can get 7/4. So any question? I think we can stop here for now. Yeah, and for next class, we'll go to the convolution property. Okay, let's have a break.我可以把第5章教完。啊，照本。啰嗦。 上次也是问那个 integral，
这个是要分
那个
是要分那个有周期没周期，是周期那就要回到第三。
等一下你要问什么？
没有，你上次说那个啊？你要说周期？你看什么？
那个 complex exponential 的 integral 是吗？我这里为什么没有笔啊？
原本有吗？
通常会有，不是吗？
哦，对。
对啊，
那个不是上聊到分，它是周期，它是周期，
它本来就是周期啊。
不是，我说它周期要回到第三章，对，是这样。
我有一个比较有趣的看法，这个东西嘛。然后呢，它都是 divergent 的，但是我们有个有趣的看法是，我们可以想象，因为它 divergent 我没办法积嘛，没有，那我们可以把它取一个极限，我们先积给我们解出来的东西。所以因为它是一直这样上下都是一样高度这样底下，所以我们把它乘个1的负阿尔法绝对值 t， 然后我们就记这个东西嘛。然后我们想的事情呢是说，那我们就把它乘个Exponential Decay的东西嘛，这样就可以记起来，对吧？这个东西我们可以记起来。然后我们想的是，我们等一下再把取这个阿尔法变成0的极限，它就变1。取到
对啊。为什么我取这个就可以取这个？那它 decay 它就所以它只有变0。
对啊，它只有变0，所以这样子这个无限大的回忆事情就可以消掉。
OK， 就把这个可以记了。
这样，然后这个就可以记嘛。这个积分的话，
这样拆3项解吧。
你就拆2半嘛，然后
2倍，就2倍啊？
好像不是2倍，
不是2倍。
0到无限大1除了，我们不用解欧米伽那的啦，就解欧米伽好了，比较好写，还是一样的。
还是把它变一下。
因为到时候欧米伽减欧米伽那就写成欧米伽减欧米伽那就好了，因为是一样的，因为都是个 concept 嘛，欧米伽，然后所以是负阿尔法 t 加去欧米伽 t， 然后再加上无限大到0的1除了阿尔法 t， 还是加去欧米伽 t， 然后
这也是负的。
真的也没差，反正欧米伽。然后那这种是可以计算嘛？t 的系数就是负阿尔法加欧米伽等于1，然后这个无限大减0，所以0是1，所以这是负1，然后这里再加上，因为无限大的减去0的，然后这里是阿尔法加欧米伽，然后这里是1，然后最后会是然后这个乘负，所以就是阿尔法平方加上欧米伽平方的2个相加2阿尔法。然后这个东西呢，我们在 frequency domain 上面长什么样子呢？它就是一个在0的地方，欧米伽的0的地方，它是除以阿尔法。没有，我们的阿尔法是 finite value 嘛？我们先说阿尔法是 finite value。
这个是里面这个是加，是加，我看看，对。阿尔法平方要取6的地方。
对，它是这样子，然后欧米伽大的地方它会以对吧？欧米伽平方的东西 decay 掉嘛？对。然后这个东西呢，你可以再去对欧米伽积分一下，然后它的 area 会是1。
你说对这个函数几分？
对啊，你可以再把它复建到无限大，用那个什么换成 tangent 的事情。
对，
对，然后加上欧米伽平方，那个我就懒得记了，d 欧米伽。 是等于1，还是等于1，然后你可以看出来，然后这个宽度大概会是omega 大概会是 alpha 感觉吧。所以你在 alpha 趋近0的时候，它就会越来越高，然后越来越这样变成它方程。
然后再丢大，然后后面就变 omega 值。对，这个好 tricky， 这个好懂。
对，大概是这样子推。
大概
应该还算是个是吧？虽然还有其他鬼事情要讲。
这是很技巧。
应该，如果你真的数学较凹的话，你也要证明说你用不管什么样的卡都不是都用一样的极限，对吧？就是可以看一下这样子，有点直觉，
这样很整齐。
对啊。
所以不一定要回到第3章那个，就是
但这样子看也是可以的，
对啊，分它是周期跟非周期。
对啊，但是
非周期我就用第4章方法做。
对啊。
问一下，为什么一定要画这个图？这图是帮助我看能量。
但是你 complex number 当然会有2个图啊，你是一个是角度，然后一个是长度啊。complex number 感觉，
所以
你要不就是画实部、虚部、标部，就是画角度、长度啊。
我是现在是我一个频率空间上的 basis， 它是其实一个圆。就是它是一个3维的，因为那个
也是可以的，
欧米伽里面有10
对啊，你要这样看也是可以的。但是总之就是欧米伽就是那个 big X 是个 complex number 嘛。那我们有一个画图方法就是画成2张图。
对。这个算高频还是低频？如果就是一个这样子算高频，一个丢掉方向是高频还是低频？
那你要
一个丢掉方向它是高频还是低频？还是
你是在什么 domain 上面是个丢它方旋
？T，
在 T domain 是个丢它方旋，所以是肯定是看的算高频吧。可是它是丢它方旋是什么都有啊。
对啊，我不知道那高频还是低频。
就都有啊。看你想要怎么定义你的高频跟低频。
因为我上定义他说这个就高频我就说这怎么我就很不值，我就说这是用复利的求出来可是我觉得复利它是一条线它到底算高频还是低频？
看你要怎么定义高频还是低频。
怎么说？
那它复利就长这样嘛，然后你可以高频低频你是用它 Fourier Transform 定义吗？可是你
这看不出什么东西，它是。
然后你可以定义怎样的方旋才叫高频的，例如说你可以说可能无限大的东西嘛，你可能说低频的部分不够多，我就高频之类的或者怎样。你可以说什么，或是什么超过某一个值之后有值就算高频嘛，或者是什么某一个值之后积分起来很大它是高频，然后可以有很多不同的定义啊，看你要怎么定义高频是怎样叫高频啊。
高频的定义
或是没有低频的叫做高频。
我知道高频是指频率很高才叫高频。
对啊，频率很高就高
不是
频，但是你既有高频又有低频的嘛，所以那就看你要觉得怎样才叫高频。对啊，这个就是比较工程你要怎么选的问题啊。
那为什么 test bench 这里是低频，这里是这样？
总之接近零的部分是低频的嘛？
为什么可以这样说？
那你是频率低就是低频啊？
就是 decrease time 的时候，只要是接近零的，就是每接近
你说 discrete time 的对啊，因为它会 periodic 嘛，对啊。
哦，
但 continuous time 就没有嘛？你的流套方式是 continuous time
就不会用那个规则，
不会有 periodic 啊，就是接近零的地方就是低，然后高的地方
就只有接近零的地方是低频，其他地方就越后面就越高。
对啊，越远就越高。
但 discrete time 不是，那就是
有这2派的事情。OK。那我们要开始。Okay, let's start. And yeah, now let's go to a more complicated property or convolution property. So you have a convolution on your. Oh wait, way big. Let's see. Oh, okay, it's big. Let me check. Okay. Yeah. So if you have convolution on your time domain, then you have multiplication on your frequency domain. And we already see this in chapter 4, so it's less dramatic here. And we kind of expect this. And but just like chapter 4, then this gives you a nice relationship between your small h and the big H. And you can use this to solve your LTI system. So we can give interpretation of this thing. So if your x is your input signal and y is your output signal, and the small h is the impulse response to your discrete time LTI system. And on chapter 2, we know this is the input-output relationship of the LTI system. And now we know if you Fourier transform this equation and go to a time domain, and then your y will get to big Y and x will get to big X, and your h will get to this big H, which you also define in chapter 3. Okay. Is h will be the eigenvalue of your system and at frequency omega. Okay, and yeah, and back and forth of the small h and the big H will once again be our Fourier Transform equation. Do we have it here? Not quite, but yeah. So, but in chapter 3, we should have how to calculate big H from small h. And that will be our analysis relationship. And now we know we want to calculate small h from big H. We'll use our synthesis equation. Okay. And let's see. So this example once again. So if our LTI system has this impulse function just being impulse response just being delta of n minus n0, then we know this will just give you a time shift on your signal, so the output will just be a time shift of your input. And but we can go through this, we can calculate the whole thing to a frequency domain and convert it back. So let's do that. So we start with the output function is the input function convolute with your impulse response. And now we do Fourier transform of everything. So Fourier transform of this delta function. We just do the calculation here. So we use this brute force calculation. So summation everything, then your function, then e to minus j omega n. Then because of this delta function, you pick out n equal to n naught. So it's just e to the minus j omega n naught. Okay. So big H is this thing. Then big Y is your big H times big X. And now we do a reverse Fourier transform back to the small y. And look at this, you find out that this is a time shift relationship. So this is HR e to a minus j omega n naught. We'll just give you n to a minus n naught. And yeah, so we go through a big loop to the frequency domain and come back to what we expected. When you convolute with delta minus n naught, then you get HR. You get a time shift on your output signal. Any question? And also we can, I guess we can learn how to construct a filter now. So we know our ideal low-pass filter should be something that filters all low frequency things. So with some cutoff frequency at omega c here. And so this is the ideal response of your low-pass signal on the frequency domain. And now we know how to calculate the response on the time domain. So the impulse response of your low-pass filter here is just the inverse Fourier transform of the square wave function. And you can calculate the inverse Fourier transform here is some finite integral. So the square wave and inverse Fourier transforms are integrating over a period 2 pi, and just times c to j omega n. But you cut off at omega c minus omega c to omega c, and you do the integral, and you see this sinc function. Okay? So the sine omega c n over pi n. So yeah, and this is HR. This is duplicate. So yeah, so now we learn how to construct a low-pass filter in terms of its impulse response. And then yeah, then not surprisingly we can use okay, this is not solving differential equation yet. But just like in chapter 4, then we can use this to calculate our LTI system output, right? So we can kind of do a convolution in a very complicated way. So we have two inputs. So we have an input signal and small h, and want to calculate its convolution. So this is something we do a lot in chapter 1, and when we do this in chapter 1, we just do the summation, and it's really quite doable here. Here we want to use our convolution relationship to do this in a bit more smart way. So anyway, so we have our two signal, which are our favorite exponential decay. Okay. Yeah. So alpha beta here, and I think we want the absolute value of alpha and beta to be less than 1 for this to be convergent. Yeah, only there is convergent. Yeah, so absolute value of alpha beta is less than 1, and you have two exponential decay cutoff at n equal to 0. And so first we will do Fourier transform of this thing, and Fourier transform of those two things, you can easily calculate it as a geometric series. Okay? Because yeah, you have exponential decay and it's over the geometric series, and and you have HR e to the minus j omega here because you are doing Fourier transform. Okay? Fourier transform gives you the e to the minus j omega n thing. So that's the Fourier transform of those two things. And I believe this we also calculate in some example. But anyway, you can calculate this thing. Then back to calculating our convolution, and from our convolution property, we want the convolution of two signals on the time domain will be on the frequency domain. You will just have the multiplication of those two spectra, and so that's a multiplication 1 over 1 minus alpha e to the minus j omega times 1 minus beta e to the minus j omega. And then you want to Fourier transform this back, but it looks quite annoying. And once again, we do the partial fraction expansion. Okay. And yeah, although it's not quite in the form we talk about partial fraction expansion, but you can do a similar thing. I guess if you multiply everything with yeah, as you can look at e to the minus j omega, kind of like x here, and you do partial fraction expansion with this e to the minus j omega. Anyway, if you do a little more scaling, then you can get this back to the partial fraction expansion form. But you can also just write it in this form. So 1 minus alpha e to the minus j omega plus a, and dividing a and another b, and over 1 minus beta e to the minus j omega. Okay. Although this is a little more complicated, it's not just omega here, but yeah, but this partial fraction expansion still works, and you can solve for a and b. Okay. And here we skip the solving, so you should cross multiply this and see how this will equal to 1. And so we just give the answer here. And do alpha over alpha minus beta be equal to beta over alpha minus beta. Then you do inverse Fourier transform back to the small y. Now this is in the form that we know. We know this 1 minus alpha e to the minus j alpha, just because we do the Fourier transform here already. We know the inverse Fourier transform back is going to be another exponential decay, with the exponent being alpha, and this transform back will have exponent beta. Okay. And you have alpha here and beta here. And you can write everything together in a little more organized way. So alpha minus beta together, then multiply alpha in, then alpha to the n plus 1 u of n, minus beta to the n plus 1 u of n. Okay. So any question? Okay. Yeah. And just like in chapter 4, this is not the total solution, because when alpha equals to beta, then you will get 0 over 0, and you need special treatment for it. So yeah, also just like chapter 4, so alpha equal to beta, then you are on the frequency domain, you have 1 over 1 plus alpha e to the minus j omega square, so something square. And you can get this form by doing a differentiation. What do we know? Okay. So this y of e to the j omega being 1 over something square is have this 1 over something, and you do a differentiation on omega, and then you get a square here, and then there are other constant terms. So all the constant things you sort it out, it will be j over alpha, and also because you do then when you do differentiation on e to the j omega, you get e to the j omega. Okay. I should say when you do a differentiation on e to the j omega, you get extra e to the minus j omega, and you want to cancel all that, so you multiply with e to the plus j omega. Okay. Anyway, so that's some calculus you can check. And we know how to then we know what happens if you do a differentiation on the frequency side, right? So we have the what is it? So we have the Fourier Transform pair we start using as the start of this problem. So the exponential decay is Fourier Transform is this 1 over e minus 1 over 1 minus alpha e to the minus j omega. Then you do differentiation on both sides, and then you do differentiation on this side, and then you get a minus jn here. And you can switch j to here, and then you compare this to this. We are almost there, except we need to divide both sides with the h alpha, and we also have h e to the j omega. Okay, and so we can multiply the h alpha here, and if we want to get the h j omega here, we can use time shift on this side. Okay, so we get a time shift of -1 here, then you get because when you get n to n minus n naught, then you will get e to the minus j omega n naught. So pick n naught equal to -1, so actually n to n plus 1 here, then get e to the j omega here. Okay. And yeah, oh, so it's doing different order. So get this form, then we change from n to n plus 1 to get the h j omega. And finally, there is alpha. We just divide both sides with alpha. Okay. And yeah, so we divide both sides by alpha, then you get this thing. And on the other side, you get your n plus 1, and alpha divided by alpha n plus 1 divided by alpha n, and u of n plus 1. Okay. So lots of calculation, but everything is what we taught today. Okay. Any question? So nothing too serious. So the big idea is you do differentiation on this thing, then you will get a square, and all the extra term you just try to account for them. And anyway. So that's the answer. When alpha equal to beta, you will have this y of n equal to n plus 1 alpha of n u. And do we? Okay, I'm not sure. Do we do this in our first midterm? But we have something. Probably skip this. Okay. Anyway. So that's it. And there is something a little more to say about this thing. That is, this u of n plus 1 looks a little weird. U of n plus 1 is something like head of at n equal to -1, right? But your x and h are both starting at n equal to 0. It's kind of, so this is causal and it started at 0, so you don't expect any response before n equal to 0. And so this u of n plus 1 looks weird, because why does this has a value because at n equal to -1? And that's because it actually has no value at n equal to -1, because when n equal to -1, this n plus 1 is 0. Okay? So because of that, so you can shift this to u of n instead. Okay. So y of n equal to n plus 1 and alpha to n u of n. Okay. Just to be something nicer looking, because you want to respect the causality of your system. Any question? And obviously you can have similar thing, and you have more power, then you need to do more differentiation, and those rules will be summarized in a table. Okay. and also probably after the midterm. We'll talk about how to solve difference equation, and you also need to do a whole bunch of partial fraction expansion. Okay. So that's the first use of convolution property to help you calculate convolution, although this doesn't seem necessarily much easier than just doing the integral. Say alpha equal to beta, then yeah, you have two square root function, and it's pretty easy to get this integral. But you can go around and use this convolution property to get this result. Okay. And okay, let's see something else. So this is an idea similar to what we told before. So in this example, we try to construct get this bandpass filter. So we start with the low pass filter here, H of low pass, and we say just a low pass filter that cut off at omega equal to power 4, and we are restricting on space here, so everything on this picture. So we say our low pass filter is just this block, so we cut off at power 4 and minus pi over 4. And now the question is, if you have a low pass filter that looks like this, then you pass your system is actually this whole thing, then what's the output? And this whole thing is, so you first copy your x into two parts, and one of them just pass through low pass filter. Another of them you do this non-LTI operation of multiply by minus 1 to n, and then you go through your low pass filter, then you do another multiply by minus 1 to the n, which is again non-LTI. You get something, then you add this together. And what's the output? So obviously the output down here is just whatever you pass through low pass filter. But let's see what goes on the upside. And this will basically shift your low pass filter to high pass filter. And we have seen a similar idea in continuous time. So here, well, let's go through this slowly. So first you x of n goes through this minus 1 to the n. And this is a frequency shifting operation. And on the time domain, you will shift your big X to big X of e to the j omega minus pi. Because minus 1 to the n is e to the j pi to the n. Okay? And everything about this in frequency shift. And it's frequency shift of plus pi or minus pi, that's the same. We say minus pi here. And so that's big omega, big W1 here. And then go through the high pass filter, and then you multiply your spectrum with the the low pass filter. Then you multiply your spectrum with the low pass filter. Then you go through this minus 1 to n again, and then you shift frequency with another minus pi. Now, so this function gets shifted by omega to minus pi on both those two omega here. So this low filter of omega become low pass filter on omega minus pi, and then this spectrum part of omega pi to omega minus 2 pi. But spectrum is a periodic function with period 2 pi, so you just back to your original spectrum. But now you have your low pass filter shifted by a frequency of pi. And we talk about this. So only in discrete case, if you shift your low pass filter with a frequency of pi, it becomes a high pass filter. Because here you are filtering all things around frequency 0. If I shift pi, then you are filtering all around frequency plus or minus pi, because it's periodic. Okay. So if I add everything together, then your output thing, the spectrum of your output, will be big W3 and big W4 together, and that's your X filter with this low pass filter, and shift to the low pass filter with your high pass filter. So yeah, this is how you construct the bandpass filter in discrete time. Question? Have time 20 minutes about time. Okay. Then lastly, we have the multiplication property, which is basically inverse of the. This is the inverse of the. Excuse me. Convolution property, but now big X has a period 2 pi. So instead of doing an actual convolution, we do this periodic convolution, which is convolution, but you only integrating over a period of 2 pi. And you normalize with 2 pi. And also we still keep our weird form of writing big X with our argument being e to the j theta and e to the omega minus j omega minus theta. Okay. But anyway, on a high level, if you have multiplication on your time domain, then you get a convolution on your frequency domain. So we have a periodic convolution here. Okay. And we go through a proof here. So proof is not too complicated. So you have y is the multiplication of your xy and x2. Then basically use this our two Fourier transform equation back and forth. Once again, our synthesis equation and analysis relationship. So first we write our big Y with our synthesis equation. So summation small y to the minus omega n. And then we can break our small y to x1 and x2. Because by definition is multiplication of x1 and x2. Then we break our x2 into the integral of the Fourier transform with this 5.8. Okay? Oh, sorry, the other way, although that doesn't really matter. So we break x1 equal to big x1. So x1 are this integration of big x1. And somehow instead of integrating, because we already have omega here, so now we change the name, right? So we don't want to we need to differentiate our variable a little bit. So we already have omega in our equation. So this integration, this omega is a dummy variable. So let's call this dummy variable theta instead. Okay. So integration and all the omega here, right now theta here. And then we do our favorite change of ordering. And so instead of the summation and integral, we do integral and summation. Okay. And so integration and summation, and the summation n, so we need to pick every term that has n. So the two sides, 2 pi can go outside and x1 can go outside. So since with n is x2 of n, and we have e to the j theta n and e to the minus j omega n. Okay. And those two together give you our minus j omega minus theta n. And so that's everything with n. And obviously we still have our integration on this theta. And now finally, we look at this equation and we compare it to this 5.9 and convert it back to big x2. And we see that this is basically same as this equation, except instead of omega here we have omega minus theta. So so we make a mistake here. And so it should be plus here to match the equation up here. So instead of omega, we have omega minus theta. So it should be x2 e to the j omega minus theta, like this thing. And yeah, so write this as x2 and look at everything around, you find out we already arrived at our equation. Big Y equal to is 1 over 2 pi and integral over interval of 2 pi x1 theta x2 omega minus theta d theta. So that's a derivation. And I guess I'll see an example. Yeah, example. So this is a little more interesting than it looks. So x1 equal to yeah, we have x equal to x1 times x2, just the form we want. And let's see. And the question is find big X. And obviously what we want to do then is, when it's already in this multiplication form, then we want to use our periodic convolution thing. And so this is set up nicely to get it easier with this convolution relationship. So our x1 is the sinc function, x2 is the sinc function. So if you want to do these proof falls, it's going to be very ugly. x1 times x2 is going to be sine something, sine times sine over n squared, and it's lots of terms. But instead we can do our convolutions. We can do our convolution formula, and because we have a sinc here and we already know the sinc function correspond to square wave in the frequency domain. I guess we didn't do this derivation, don't quite remember, but anyway, this is true that if you have a sinc in the time domain for discrete time, then actually we see this, right? This is those are the bandpass filters. Sorry, those are the low pass filters. Right. So if you sinc in time domain, and they will have the, so we just have the zero. Yeah, so this thing, so if a sinc on the time domain, and will be those low pass filter on the frequency domain, which is also square wave function. Okay. So we have two low pass filter tying together, multiplying each other in the time domain, and let's see what happens in the frequency domain. Okay, and it should be this convolution. And okay, and now we do something weird but makes sense. That is, we define another function that's x hat. That is, you cut out x1. So that is x1 hat is you cut out x1 with only one period. And here, because we know x1 is going to look like this low pass filter that keeps repeating itself every 2 pi and has some block around 0, so we cut off around minus pi to pi. Okay, so we just cut off one block of this low pass filter. Okay, so this is x1 hat. And why do we want to do this? Is because it's a nice way to represent it's a nice way to represent this cutoff at minus pi to pi. Okay? So in this formula we have this integration from minus pi to pi x1 and x2, and now because x1 equal to x hat on this minus pi to pi interval, right? It's theta between minus pi to pi. x1 equal to x hat, So we can write, instead of writing x1, we can write x1 hat. And then because x1 hat is 0 outside of this minus pi and pi, then we can write the integral. This is as the integral from minus infinity to infinity x1 hat. Okay. So first you change x1 to x1 hat to cut off all the extra things of x1. And now instead of this convolution only on a period, you can have a real convolution from minus infinity to infinity. Okay. So now you can just think what's the convolution of this x1 hat to the x2. Okay. And here, okay, we skip a little bit. Also skip the sync relationship, which we just give us a formula here. So you have this x1 and x2 both being sync, and in terms of our cheat sheet here, we have with sin w n over pi n. Then its Fourier transform is low pass filter on the cutoff being w. So x1 is this and x2 is this. And you compare that using the w1 equal to pi over 2 and w2 equal to 3 pi over 4. Okay. So big x1 will be those low pass filter with the width plus minus pi over 2, and x2 is this filter with width plus minus 3 pi over 4. And anyway, so back to our periodic convolution. So we can think about periodic convolution. We see that periodic convolution is actually a convolution of the second signal of one signal, which are periodic, and just one period of one of the signal. Okay. And this makes sense because you don't want to multiply too many things because it's finite. But you also want this output to be also periodic in 2 pi. Okay. Because it's big X. Once again, remember this is the Fourier transform of a discrete signal. So this big X should also be periodic with period 2 pi. And you can kind of see from this formula the convolution with a periodic signal with something as finite. So you're going to get something finite and periodic in 2 pi. And well, now we skip the calculation. We just plot the answer here. So convolution of a square wave signal is not too hard, and you can kind of do the overlap thing, right? So if you pull this block in both sides, and the more and more you pull it more on this side, then you will get a linear decreasing. That's why you get a slope here. And when your x1 is kind of in this side, and you get the minimum value, and that's the flap here. And also if x1 hat and x2 are totally overlap here, you get a flat here. Okay, and so you will get those really nice, really simple signal of just some straight lines together. And once again, it's periodic with period 2 pi. Okay. And I think that's it. So any question? So that's an example of periodic convolution. You also get something periodic because you can think it as a convolution of a periodic signal and this head function, which is one period of your first signal. Okay, and I guess we'll go through our cheat sheet, then stop today. Okay, so cheat sheet. So first is the properties. Once again, I forgot to list the Fourier Transform formula. But anyway, so property of Fourier Transform. So first you have linearity. in a linear combination on your signal, then Fourier transform will also be linear combination, and then your time shifting, you get minus a naught here, then you get e to the minus j omega n naught. Frequency shifting, you get plus j omega naught n. And then conjugation, just like the continuous case or all other case, you get conjugation, and negation in frequency. And also time reversal, give you frequency reversal. And now time expansion is weird because first you cannot do compression, and the time expansion you can only expand with some multiple of k. And when you do this multiple of k expansion, then you get the squeezing in your frequency domain, so you get k multiplying your omega. And also the two relations we just talked about, so convolution and it is a little small. Let me zoom in. So it's two zooming. Okay. So convolution, then convolution on time domain, then you get multiplication on frequency domain, also multiplication on time domain, then you get this periodic convolution on the frequency domain. And also difference. Difference is once again very easy. It's a linear combination of this time shifting. So just get is 1 minus e to the minus j omega. And the accumulation is the reverse of frequency. Is the reverse of the difference. But you also get this weird delta function term that basically you just need to remember. It's like it's a good way to memorize this is the terms that look like the u of n. Okay. So yeah. So if some terms like u of n, your accumulation, then when you do Fourier transform, you will get this extra delta function times pi. And also you can just do differentiation in frequency, and we'll get a minus jn on your time domain. You can do minus j to plus j on the frequency side. And then you have a symmetric property. Conjugation, if xn is real, then those are same as a continuous time. And also if xn is real and even, then big A is real even. And x is real and odd, then big A will be imaginary and odd. Okay. And okay, and then you have a real odd decomposition. Sorry, even odd decomposition. I think it is the same as the upper thing. So it's the same thing, so let's not go over again. And also finally you have possible relationship. So energy in a time domain equals energy in a frequency domain, but you need to divide by 2 pi. And the integral is only over a period. And okay, now this is really small, we need to do in. Okay, and there are some nice Fourier transform pair that we should probably remember. So first is if the signal if the signal is a periodic signal, you can write it in Fourier series. Then we have this really nice equation for its Fourier transform. You write down summation over, but the weird thing is the signal you only write in the summation of k for n values, big N values, but in the Fourier transform, then we want x is something from minus infinity to infinity. So now the k is from minus infinity to infinity, and you have ak, which ak is periodic. And the delta function at value 2 pi k divided by big N. Okay. And the Fourier series coefficient here is ak. And also the spatial case of this thing is just one frequency, so just e to the j omega n. I guess not quite the spatial case because omega naught can be not rational. Okay? So if it's rational, then it's a spatial case, and you get 2 pi and summation delta omega minus omega naught plus minus 2 pi L. And so if omega naught is not rational, then it's a spatial case of this thing. And just ak equal to 1 for one of those. And it's a little weird is that when omega naught is irrational, so this is actually not a periodic function, but yeah, not a periodic function in discrete time signal sense. You still get a delta function. So yeah, that's what happened. And also you can have cosine and sine. You can write cosine and sine in terms of exponential. So obviously you get those 2 delta and difference of 2 delta, and it's both of them become imposition. And now kind of a reverse of this thing. Actually not quite reverse. And also you can have xn just being a constant. Then that's like setting omega naught equals 0. So you just get this delta of omega minus 2 pi L. Okay. And the next page. Okay. Next page. Okay. Now we have. Oh, sorry, we are still in our divergent case. Okay. So the periodic square wave is once again still periodic. Then you have this delta chain, and this ak will look like not quite sig function, but something really similar to is sine over sine. It's higher frequency on the top. And finally you have this imposition, and you have this imposition, where this imposer is finite height and this imposer is infinite height. Okay. And finally, we have our latest divergent example, and there are really only 2 of them. So one of them is this exponential decay, which will give you is 1 over 1 minus a e to the minus j omega. And we're going to see a whole bunch of them. And also, you should really group these together. And also, if you're different, you want this thing to some power. So it's 2 or as power. Then you will multiply some polynomial in front of your exponential decay. You get n plus 1 or n plus r minus 1 factorial over n factorial. Okay. So that's a nice formula to know what are the inverse Fourier transform of this thing. And okay, we are over time, but then it's really quick. So just you have a square wave here, then you have a sink, and you have a single wave here, and you also have a sink. Oh, sorry, you have a single wave in time domain, then you don't quite have a sink here. It's a sine over sine, we said. And you have a single wave in your time domain, which is also periodic. Then you get a sink in your time domain. And then there are delta function and state function. So that's it, and we'll probably have a review next Tuesday, and yeah, good luck on the midterm. Okay, question? Okay, let's stop.